It's like you watched the video yesterday. All right. Did you? Okay. All right. Let's do this example. This is going to be the same model. All right. We're going to use the chi-squared model again. Yesterday, we did the goodness of fit test. All right, where it was one variable, and we had a certain number of categories to see if it matched some model or some claim that's being told to us. Today, it's still going to be one variable, but now we're going to see if we have homogeneous groups in terms of that variable. So in this case, we have 90 subjects in an experiment are being randomly assigned to one of three treatments. Either they're getting a placebo, either they're getting a natural remedy called the St. John's wort, or they're getting this prescription drug, Postrex, to help treat their depression. All right, so this right here is called a two-way table. We first saw this in August. If you guys can remember all the way back. It's a two-way table, or called a contingency table. And whenever you see this and you're running a test, it's most likely going to be a chi-squared test. Okay? So that's this right here. So you can see this is the actual data values that were given to us in terms of those 90 people. All right, so let's first come up with our hypotheses. All right, what do you guys think we're going to think is the best idea right now? Anyone? Any thoughts? We're trying to treat depression three ways. A placebo, right? Remember what placebo is? Like a fake sugar pill. Okay. A prescription drug, right? Or a natural remedy. So right now we're going to assume what about all three of these ways to treat depression? They're the same. All right, so I'm going to do that. Remember, think in your word homogeneity, right? Homogeneous. When you think about the word homogeneous, what do you know the word homogeneous to be? Right, the same, okay, for our groups. So I'm going to say the rate of recurrence for depression is the same for all treatments. Okay, so right now, do we think one is better than the other? No, we think they're all the same. Right? What is the alternative going to state? That they are
better than.
They're not the same, right? So in some way, whether it's one is better than the other, Thomas, or whether a couple are better, whatever it is, it's just not going to be homogeneous. All right, that's what we're trying to prove. Right? The rate of recurrence for depression is not the same. And I'm not going to say for all, because it may be for just some of them. I'm going to say not the same for some treatments. Really, it just needs to be one. If one of them is not the same, that should be enough for us to have enough evidence to say that they're not the same. Again, so I know Joseph and Diana, you guys weren't here yesterday, but this is a new model, the chi-squared model. We are running 3 different tests. Today is test number 2 with it. Right? And what you should notice is that with the hypotheses, here it comes. Right? With the hypotheses, right? It's all sentences. Victor, I'm sorry. Did I not give you the stuff? Oh, you were absent too. My bad. So Victor as well, you can see that the hypotheses is all words, right? No symbols, nothing like that. All right? Now, after we do the hypotheses, we're going to go straight into the assumptions and conditions. What's that first assumption? Independence. This is the wrong one. I'm going to do the right one. Did I give you the wrong one? I did. Okay. All right, so what are we assuming about these treatments? What are we assuming about these treatments? That they don't affect each other. So if some person who's in this study claims that their depression has returned or that it has not returned, are we going to say that's going to impact anyone else? The hope would be no. All right, so I'm going to say each treatment's results will not affect others. Did it mention randomness?
Randomly divided. Right?
Excellent. So if you guys think back to your days in, I think it was probably November, December, a phrase that I wanted you guys to be on the lookout for the AP exam is random assignment of your subjects to treatments. Random assignment of your subjects to treatments. What should that be cueing in your mind? That it is an experiment. Well done, Victor. It's an experiment. If you randomly assign, whatever it is, in this case, people, right? Randomly assign your experimental units to different treatments, that is a surefire giveaway that this is an experiment. All right, so randomly, I think it's 90 assigned 90 subjects. Okay. Now I put here on the 10% condition. All right, the issue, or not issue, but because we're doing experiments and this is not a sample, that all of these issues with sample size are not really that important here, right? So I don't really need to check the 10% condition because we're not going to take our results from this and try to generalize it to the public, right? You want to be careful or cautious if you're going to do that. All right, we need to make sure that our data comes from categorical variable, right? In this case, yes, we're talking about the different treatments. The sample size assumption, you can write that 90 is a large enough sample. I'll write it. But again, does this really make sense here? No, this is an experiment. The thing that I always look out for when I do or read about experiments is I want to make sure that the people that are in this, right, the subjects that are in this study or this experiment are actually experiencing what they care about. All right, and what do they care about with these people? Handling depression, managing depression. So if someone is not dealing with symptoms of depression or clinically diagnosed depression, should they be in this? No, right? So we want to make sure that we have, if the people are afflicted with whatever we're talking about, that's fine, they could be in it. All right, so just keep that in the back of your mind when you read about these different studies, okay? Now, we did this yesterday, the expected cell frequency condition, right? We're looking for our expected numbers to be 5 or more. I'm going to show you 2 ways to do it with a two-way table. I'm going to show you the really clunky way, lots of math, lots of big numbers, right? And then I'll show you with the calculator. Most of you will probably end up using the calculator, all right? So the first thing I want to do, you guys see the table? Go ahead and fill in. Can you guys put 2 numbers in each cell for me? All right, let's put in the numbers it actually gave us. I think this one was at 24, and this one was 6. And then I think it's 22 and 8 and 14, 16. I think those are from the first table. Okay. Now they've already gone and given you totals for the rows. You see how they've added those up to give me a total of 60 people are claiming their depression returned, and 30 are saying that they have no sign of depression after being a part of the study. Let's get the totals for the columns. All right, so what would be the total for my placebo column? There, I think Australia saw it. Was it you, Australia? Oh, Carolyn. My bad, Carolyn. They're all 30 is right. So all of my 3 column totals are also the same of 30. All right, now I need one more total. I need what is called the grand total. Do you know what the grand total is? It is 90. Always think about how many people are here. Now, just be careful. I'll get people every time I do this. Let's say, well, add up all your totals. Just be careful, right? If you do that, that's 90, and this is 90. So if you say it's 180, you would be incorrect. All right, so make sure to ask yourself how many people or whatever you're dividing up, how many are there? All right, so here's how you can find the expected numbers with just math. You can do row total times column total divided by grand total. Okay, so let me do one for you. And you knowing that, row total times column total divided by grand total, might actually give you one question correct on the AP exam. All right, so I'm going to do the expected value for the people that are taking the placebo drug and are saying that their depression returned, right? We know that it's actually 24 people. I want to see how many do we think it was going to be. Okay, ready? So what is the row total? 60. So I'm going to write down 60. You can write this down or not. It's up to you. All right. What is the column total? 30. And what is the grand total? 90. Does anybody know 60 times 30? It's 1,800. All right, and if you take out a 0 from each of them, what do you think you get? You get 20. We're okay with that? So in this case, for the placebo, we actually ended up seeing more people that said their depression returned than we expected. We expected only 20 people. How many actually said they are experiencing depression again? 24, so 4 more. Okay. Let's do the same thing for the natural remedy, the St. John's wort. Right? What is the row total?
16.
What is the column total?
30.
What's the grand total? Oh my gosh, the same. They are. I don't want you to think, Carolina, that it will always be true. In this instance, it is. Yes.
If they aren't the same like this, it's completely fine.
Totally fine if they're not the same. You're going to do it on the exit ticket. Spoiler. They're not the same. Okay. All right. Can we do the next row for those that had no sign of depression? Okay. So what would be our row total for this one? 30. Column total, 30. Divided by grand total, 90. I'll do that work again. It is going to be 10. So that's 900 divided by 90, which is 10. You're going to see it's the same for all 3 of these as well.
We don't need to do the actual equation as long as we have one. Right?
You're actually going to see you don't need to do that at all. I'm going to show you in the calculator how I can do it for you. But I just want to show you if you feel like you want to do it by hand, you can. Row total times column total divided by grand total. Works every time.
Is there a way for us to know that it's going to be the same without having them memorize the second one? Just looking at the problem, so big time.
I think the moment you see that the column totals are the same, that would be the giveaway for me. Yes. Okay, go to the next slide. Oh, I should have mentioned while we were doing that. The point of doing that was, what do you notice about my numbers in red? They're all at least 5. That's the check we're doing to make sure that we have a large enough sample here. I know it's not really applicable since we're not doing a sample, but we want to make sure they're all 5 or more. In this case, they're all 10 or more, so that's good. That is large enough. So I'm ready to write my statement. Right? The conditions have been satisfied. So I will use the chi-squared model with, I know Joseph, Victor, and Diana, you weren't here yesterday, but when you do the chi-squared model, similar to the T distribution model, you do need to mention 8 degrees of freedom. All right, there are an infinite number of models for each of these. All right, so the way we do it with a two-way table is we take the number of rows, subtract 1, the number of columns, subtract 1, and multiply those 2 numbers. So this right here is how we find the degrees of freedom. All right, so how many rows? 2 rows. How many columns? Be careful not to include the total. 3. So 2 minus 1 is 1. 3 minus 1 is 2. 1 times 2 is 2. So with 2 degrees of freedom. To run a test for homogeneity. Now, I'm going to take you guys through the long way. It's not really that long, but I'm going to take you through the long way of doing this by hand. And then once we finish the whole problem, I'll show you how to do it just in the calculator. Okay? In my experience with these types of questions on the free response, at least the AP exam is nice and they keep it small, right? They keep it manageable if you do want to do it by hand. All right, so you'll notice on this slide, I've placed 2 two-way tables, okay? This one is where I want to write the formula. Do you guys remember the formula for how we find the chi-squared components? Observed minus expected. Well, hold on before you do the over. You got to square it. I mean, Victor was even here. I love it. Over the expected, right? Remember the way you're going to memorize it? Exactly. Clearly you didn't watch the video. All right. So we had 24, you're good, 24 people that are taking the placebo that said their depression returned, right? That's actually how many people we found, minus how many people we expected, 20. Don't forget to square it, over 20. We square it, yes. Should we explain to Eduardo why we square it?
So we don't get no.
Well, and this one would have been positive, but you can see later we'll get some negatives. Start adding them together, positive and negatives, they're just going to cancel each other out. So to get around that, we square it. And also remember, we're trying to find the chi-squared test statistics. That's kind of where that squared comes from. All right, next one was, I think it's 22. Right? Oh, gosh, 22. Oh, my brother's 32 today. Gosh, what a day. And then this one today, 14? Is it 14? I think it's 14. Now, the nice thing is that if you do forget this formula, you don't actually need to have it memorized. It is on the AP exam formula sheet. So that's one of the few that they give you, which is nice.
Wait, the denominator is also the expected.
Always, yeah. Oh, We can make a song if you really want. Put it on the channel. All right, 6 minus 10 squared over 10. 8 minus 10 squared over 10. And 16 minus 10 squared over 10. I think we can do this without a calculator. I feel pretty confident in your abilities to do mental math. All right, 24 minus 20. 4 squared. 16 20ths, reduce that, you get 8 tenths, right, which is 0.8. Yes, I know I could reduce more, but out of 10 is easier. Yes, everybody okay? It's 4/5.
Yeah.
Let's do the next one. 22 minus 20. 2 squared. 4 20ths, reduced to 2 tenths. 0.2. And the last one for the depression returning, that's going to be 36 20ths. Divide that by 2, you get 18 tenths, which is 1.8. So right now, out of these three, what's going to be driving our chi-squared test statistic? The last one. You can see we expected 20 people to claim that their depression returned, when in fact we only saw 14. So that was much less than we expected. Let's do the next row. 6 minus 10, square that, you get 16. 16 divided by 10, 1.6. Do the natural remedy. That's 2 squared, 4 tenths. And the last one, it's pretty large, 3.6. Can we add those together? Yeah, we can. You ready? Let's see. What pairs do you make in your brain to make this easier to do mentally? Anyone?
0.0.
Oh, I was gonna say these two. Nice. So you thought those two? Okay. I was gonna do these two and these two. That's fine. We can do that
And
one.
then 0.4 and 3.6.
Yeah. I like it. So what do you get?
2.8.
No.
What?
8.4. You're good. If you're wondering where I got that, I just added them all up. All 6 numbers added together is 8.4. Remember to draw your curve. Does anyone want to tell Victor and Diana and Joseph how it looks?
Skew to the right.
Very good. Skew to the right. Which way do we always shade?
To the right.
To the right. We can never have a negative, right? It's chi-squared, so it'll always be positive. That's why we don't have to worry about one tail or two tail. We do need to use a calculator. You're right. Oh, gosh, I lied. We do need to turn it on. But we're going to find it the old-fashioned way. Technically, we could use this. I know, Thomas, you brought this up. We could actually use the appendix from the book where they have the chi-square tables, right? That would be even before my time. You don't have to use the tables. My teacher used to make me have the tables in a binder and like refer to them to find out what the p-value was. And I was like, Mr. Poole, we have a calculator. He was like, no. Okay. Second Mars. missed the second. There it is. All right, we're looking for chi-squared CDF. Chi-squared CDF. You see number 8 is chi-squared CDF. Right, we've used normal CDF. That was the very first one we did back in probably September, October. Then we used T-CDF recently, right, just before break. So chi-squared CDF. What's the lower bound? 8.4 will always be your chi-squared number. The upper bound will always be infinity. How many degrees of freedom do we have? 2. And we paste it. P-value is 0.015. All right, so what is that going to tell us?
It is below our p-value. So
No, our p-value can't be below our p-value. Very good. No worries. So I will reject the null hypothesis in favor of the alternative. So what am I saying about these treatments? I'm almost done. Yeah. Give me like 3 minutes, bro.
Not homogeneous.
Okay, let's put it into the context.
Results are not homogeneous.
Right. I would actually go back to the hypotheses where I said the rate of recurrence of depression is the same for all of these treatments. That's the null hypothesis. We're throwing that out, and we're saying that the rate of recurrence for depression for these subjects is not the same. That's all you got to say. All right. So the rate of recurrence for depression for these, you can see outside. I'm just going to say for these 3 treatments. Is not the same. Now that's all you need to do to answer this question fully. All right, I'm not there yet. I do want to show you how to do this in the calculator, Thomas. I do want you to pay attention to that as well. One more thing, I mentioned this for the test yesterday. They might ask you about which component or which cell is driving the chi-squared number. I kind of already talked about that a little bit. But if you went back up to your calculations, right, you can see out of 8.4, 3.6 is getting close, not there, but getting close to half of that number, right? So a lot of your 8.4 is coming from that 3.6 number. So just be aware they might ask a question, all right, in terms of what is driving the chi-squared number.
Do you have to do the math for that, or can you just say which one?
You do not have to do that. Well, let me answer it this way. Let me make sure everybody has this first. Okay. I'm going to answer it this way. It probably will be sometimes when they do these types of tests on the free response section, they will have like a part B or like, a little part at the end that asks, something about what is going on with the chi-squared component. So you'll probably have already done it, or remember like yesterday, hit the arrow to the right and you can see which one is the largest. Remember like we did yesterday, right? You're going to see in a moment that doesn't work with these types of tests, homogeneity or independence. You got to actually do the work though. All right. Okay. So turn your calculator on. Let me show you how to run all this stuff with the calculator. So we've never done this one before. You're going to hit second x to the negative first power, which is matrix. Second matrix. We're going to make a matrix. Matrices.
That's not the one I did that in.
No worries. Second matrix. Go over to edit. All right. I'm going to edit letter A. Anyone you want, I'm going to choose A. All right. What are the dimensions of our original table? How many rows? How many columns? It's rows then columns, right? So I believe it's 2 rows, 3 columns, right? RC Cola, I think your favorite beverage. Right, and type in what we know. 24, 22, 14, 6, 8. Yeah, I know, we've entered the matrix. 16, It should enter at the end. So you make your matrix. All right, essentially it's just the table they give you. Then you're going to go to stat tests, right? So we're going to actually find the test. So hit stat, over to tests, and you want to scroll down until you see chi-squared test. Remember, which one are we not choosing? We're not choosing chi-squared golf, right? Because what is that for?
Goodness of fit.
Very good. Goodness of fit. This is not a goodness of fit test. You'll know if you make a mistake because you go to it and be like, wow, I don't know actually what I would type in there. So two-way table, not goodness of fit. Two-way table, not goodness of fit. All right, where's my observed? A. So if you, Victor, put it in D, did you put it in D? Okay, if you put it in B for observed, you need to hit second matrix. I'll do it with you. Second matrix, and you see where it says name? You need to go down to whatever one. Let's say I put it in D. It might not let me. And put it in there. Okay? I don't want that, right? That's bad for me. Yay, people! Person. Why do you have two? Official. All right. Expected doesn't matter. It's just going to put it there. So hit calculate. Are you surprised by these things?
No.
Hopefully not. We already found all those. And then here's the fun part. You ready? It put my expected values in matrix B. So if you hit second matrix and just scroll down, don't go to edit, but just scroll down to wherever you put it, which I put mine in B, and hit enter on number 2, and hit enter, there are the expected values. So I can do it for you. All right? So you don't have to do that row total times column total divided by grand total. You obviously can, but here's a faster way. It's totally faster if you've got the actual stuff. All right. Gosh, that was awesome.